All right, we're going to go over 4.3b, optimization and modeling. And by optimization, we're trying to maximize or minimize something, right? And to do that, we very well need that first derivative. So let's look at this example. A sheet of cardboard 3 feet by 4 feet will be made into a box by cutting equal size squares from each corner. So basically, if we look at this picture, we're going to cut these squares that each have sides of x. So when we build the box and fold this thing up, this will be the length of the box, and it's the 4 feet, but it'll be minus 2x, won't it? And this is the width, 3 feet, minus 2x. All right. What is the quantity to be optimized? It's the volume of the box, right? Draw a diagram, assign variables. So basically I have a length here and I have a width here. And I know the volume of the box itself will be length times width times height, right? So let's move on. It says create a mathematical model of the quantity to be optimized. Well, if we take, and we want the largest volume. So the volume, this is what's to be optimized, right? But if we look at our picture, I'm going to back up. We have a length, we have a width, and the height is actually x. When you fold these sides up, this will be x, 4 minus 2x, and this side right here is 3 minus 2x. So length times width times height looks like this. Volume equals 3 minus 2x, 4 minus 2x times x. Okay? Now, to me, it looks like there's an open interval for this, where x can range from 0 up to 1.5. Let me back up. I got the 1.5 because if x is actually 1.5, we'll lose the entire width of the box and there'll be no more box. If x is 0, there'll be no height and there'll be no more box. So this, I believe, is an open interval. So if we take this and we multiply it out, we end up with 12 minus 14x plus 4x squared. And then I'm going to multiply through this x. All right. Now, truly, to optimize, I need to take the first derivative and find the critical points, right? So let's take the first derivative here. It's going to be 12, right, minus 24x plus 2x cubed. It didn't look good. All right. So in this case, we set this equal to 0. It was very difficult to try to factor this thing, so I ended up using the quadratic formula. First, I was able to factor out a 4, and when I divided both sides by that 4, it basically went away, right? So I'm starting with 3x squared minus 7x plus 3 equals 0. So, quadratic formula. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So x equals 7 plus or minus the square root of 49 minus 4 times 3 all over 6. 7 plus or minus about 3.6 over 6. So I end up with two answers. Notice this one's outside that open interval I had here. We cannot have a side that big. So I think the critical point in x, which will be the maximum volume, right, should be when x equals the 0.057. And then if it says what is the maximum volume, I'll go back to this equation where up here. So I'm going to say volume equals 3 minus 2 times that 0.757, right? 4 minus 2 times 0.57 times 0.57. And we do get a volume of 3.03 cubic feet, which is what the teacher had as the answer. So I feel good that we got to his answer. All right, moving on. We have another problem. This says we want to build a swimming pool with this area, and they want 5-foot decks and 10-foot decks. Find the dimensions of the smallest piece of property. So we're going to minimize the property, right? Let's draw ourselves a diagram. We have a pool that has a length and a width. Along these sides we have 10, don't we? And along these other sides, those are 5. So if I look at the area of the whole property, it's going to look like this. The area of the entire property, which includes the decks. I have length. This whole side here is length plus 20, isn't it? And this side here is width plus 10. Now they gave us some relevant information so that we could eliminate all but one of the variables. Their relevant information is that L times W of the pool has to equal 1800. Therefore, I'm going to solve for W. It's going to be 1800 over L. And I can plug that back in. All right, so if I plug it back in, I get to something that looks like this. L plus 20, 1800 over L plus 10. Then I FOILed, okay? First, L times 1800 over L is 1800, outer plus 10L, inner plus 3600 over L, which I'm going to write as L to the minus 1, and last is plus 200. Right? And if I simplify that, I get, this is my area. I get this to be 10L plus 3600, 3600 L to the minus 1 plus 200. That's my area. I'm going to move to the next page and rewrite that. So again, we got this total area formula. This is what I want. 10L plus 336,000 L to the minus 1 plus 200. That's my mathematical model. I've eliminated all but one variable. So in order to find the critical points, I have to take the derivative, don't I? So it's 10 minus 3600 L to the negative 2. And then the 200 is 0 when we take the derivative. So this is what we have. And I can rewrite it like this. 10 minus 36,000 over L squared. And that equals 0 for our critical point. So let's solve it. We get 10 equals 36,000 over L squared. 10L squared equals this. L squared equals this. If I take the square root of 3600, I get that the length needs to be 60. All right, well, that's the length of the property plus the, that's the length of the pool, isn't it? If I go back and draw my picture, this was length, this was width. I had 10 here, 10 here. I had 5 here, 5 here. So the length of the pool is 60. I did know that the width of the pool was 1800 over L, right? So 1800 divided by 60. I just want to make sure I don't mess that up. That's 30, so the width is 30. So the dimension of the property itself, right, it's that length plus the 20, so 60 plus 20 times the width plus the 10. So 80 feet by, this was 30, 40 feet, which we got his answer, which makes me feel good. Feel better than if I didn't get his answer. All right, next example and final. So there are 50 apple trees in an orchard, and each tree produces this many. For each additional tree planted, the output drops by 80 apples. Well, currently, they have 50 trees and there are 80 apples. 800 apples, I'm sorry. So they currently have some output of 50 times 800, right? Let's say 40,000. All right. So we're going to say we're going to make a chart to help us put our equation together. So I have trees and I have apples, right? So trees, if I have this many trees, I get that many apples per tree. If I add one more tree, I lose 10 apples. So for each tree I add, I lose 10 apples. So I'm going to say 50 plus a tree means 800 minus 10 times the number of trees. That's going to be my output, isn't it? We call it A for apples. So my apple output looks like this. Now I do actually have I could call this a closed interval. I could add 0 trees, or if I figure out how many trees, the maximum number of trees I could add, which would give me actually a 0 output, that's, what did I say, 80 trees. At 0 trees added, I have this 40,000 output. At 80 trees added, I have 0 output. All right. Assigned variables, we have this equation. What we want to do next is find the critical point. So let's multiply this out. So apples equals 40,000 plus 800x minus 500x minus 10x squared. If we simplify it, it's 40,000 plus 300x minus 10 squared. All right, the apple derivative is, this goes away, we get 300 minus 20x. All right, let's move to the next page. So we just did our derivative equals 300 minus 20x. I'm going to set that equal to 0 and find critical points. 300 equals 20x. X should be 300 divided by 20, or 15. Whoops. Yeah, so I'm going to take the critical point on the domain. This x equals 15. And then I'm going to test the output at when x equals 0, like I said, and x equals 80. We said this output is still, this was 40,000, isn't it? This new output, if I plug 15 into my equation for A, which was 50 plus x, 800 minus 10x, I find that I'll have 65 trees times 800 minus 150, right? Oops. And I end up with an output of 42,250 apples, and then this output is 0. So I have found that I can have a maximum yield. My maximum yield is that 42,250, and it is from 65 trees, because x was the number of trees we added to 50, wasn't it? To the 50 trees, so I have 65 trees, and I get that output of apples. So he's trying to give you a process to follow to make sure you understand the question. You've got to figure out what you're optimizing. You're going to have an equation for the object you're optimizing, as well as some additional information that allows you to eliminate all but one variable. And then in order to find the critical points, we have to take that first derivative and set it equal to 0. All right, so take a look and see if you have any questions. See ya.